So now let us see some of the important types of work we usually see in thermodynamic applications. The first one is the electrical work, and second one is the displacement work, third one is the shaft work, fourth one is the spring work, and then you have the work done on elastic solid bars. Then you have the work associated with the stretching of a liquid film, and then you have work done to raise or to accelerate a body. So these are the different types of work we usually see, but we will mainly discuss about these four, that is electrical work, displacement work, shaft work, spring work, etc. Okay, first let us discuss about electrical work. Okay, so electrical work means, see, you can see that this is our system. uh, so system, and you have an electrical wire that is passing through the system. It has got a resistance R here. So you are applying a voltage here, and because of this voltage a current passes through this resistor. Okay, so when the current passes through this resistor becomes hot, and energy from this resistor is transferred to the system in the form of heat. Okay, but you can see that from the outside energy is transferred to the system in the form of work only. Okay, because you can see that a work is said to be done when the force is acting through a distance. Here the force is the electromotive force, EMF. This EMF is causing the electrons to move across this resistor. So that is why there is a work transfer from outside to the system, and this is called electrical work. Okay, here the uh, force acting is the electromotive force. Okay, you can see that this energy transfer does not occur due to the temperature difference. It is not due to temperature difference. But see, this all depends upon how you are taking the system. So if you are taking the system like this, okay, so that means just outside the system boundary, okay, just outside this resistor. If we take a region just outside this resistor, see here energy transfers from this resistor to outside in the form of heat, because that is due to the temperature difference, because the resistor gets heated, so it has got a high temperature, and resistor gets heated, so energy transfers from this resistor to outside in the form of heat. But energy transfers from the outside of the system to inside of the system in the form of electrical work or the electromotive force. So this is all about electrical work. So maybe this is an example is the water heater. See, water heater, you are heating the water through electrical energy. So there is a work transfer from outside to the water heater if you are taking the water heater as the system. Right? So this is one example of electrical work. Now we have the displacement work, or we will call it PDV work. Uh, so let us see. So so let us take a system here. So here the system, you have the gas here. It has got a pressure P1, and you have the volume V1. Now because of this, see, this gas has got a pressure, that is P1, and this pushes the piston to the right side. Okay, so during this process the pressure gets reduced to P2, and volume gets increased to V2, volume V1 to V2. See, since the piston here also there is a force acting through a distance. You can see that this force here the gas pushes. So this is a force acting through a distance. So this is the distance covered. Okay, it moves through a distance. So then you can see that there is a work done on the work is energy is transferred from the system. So if you take this as the system, gas as the system, so there is energy transfer from the piston gas to outside, and that is in the form of work, and this is called displacement work, because here there is a this much portion is displaced. Okay, there is a it is displaced, that is called displacement work. So Let us plot that in a PV diagram. Here in the y-axis you have the pressure, and also in the x-axis you have the volume. So let us take the initial state 1. That means it has got pressure P1 and volume V1. And you have the state 2, it has got the pressure P2 and volume V2. Okay, so see, this is a quasi-static process. That is why we are able to draw the solid line. So this system changes states from 1 to 2. You can plot that in the PV diagram. Here is the PV diagram. And so how will you calculate the displacement work? Say displacement work, say let us use the formula, that is dW. See, it's not this inexact differential, we will see W is equal to force acting through a distance, that is dl, distance dl, and this force is equal to pressure into cross sectional area. So that means this is the cross sectional area. Okay. This is cross sectional area, this is the pressure. Okay, pressure into cross sectional area into distance, this is the distance moved, it is displaced. Okay, so this A into dl is can be written as A into dl can be written as dV. A into dl is the dV, or the displaced volume. This is the volume displaced. Okay, because area into distance, that is the volume. So this is the displaced volume. So you can see that W12, that is work done, is equal to integral V1 to V2 P dV. Okay, integral V1 to V2 P dV. That means initially its volume was V1. Now the final volume is V2. So integral V1 to V2 P dV. So see, you can use this formula only for a quasi-static process, because only in a quasi-static process the intermediate states can be defined. Then you can know the pressure in the intermediate states. Okay, so this is the formula for calculating the displacement work, integral PdV. Now in a PV diagram, this can be easily calculated as the area under this line 1 to 2. Okay, this area under this line 1 to 2 is the displacement work. So you can make use of the diagram to calculate the displacement work. Now we will see what is a shaft work. See, here you can see that a shaft is put across the system. Okay, the shaft is put across the system, and this shaft has got a fan or paddle at the end. So when the shaft rotates, here this rotate, you need an energy to rotate this fluid. Okay, that is supplied from outside, and this energy is transferred to the fluid. Okay, and this is called the shaft work. This is called the shaft work. Now you have the spring work. So you can see the spring here. So how to calculate? See, here also you can see you have a spring here. That means you so if you take this as the system, when you apply a force here, so it extends by a distance x. Okay, so initially it is dx. So that means you are doing a work on the system, and this is calculated using the formula integral F into dx, and this F in turn is equal to K, this stiffness K, spring constant K, into x. So if you calculate it, this is half kx square. This is equal to half kx square. So this is how you calculate the spring work. And then similarly you can calculate the work done on elastic solid bars, because elastic solid bars can be assumed as a spring. So that means when you apply a force, you can easily calculate the work as integral 1 to 2 f dx. So here you have the, see, F is equal to the stress into area. Okay, sigma A into dx. So you can calculate the work. So these are the different types of work.